Okay, it's recording. That time is wrong. Okay, right. But if I recorded. Okay, so what I want to do today is maybe. Okay, guys, bear with me. I know some of you have seen this stuff, but let me actually bring a particular thing. Sets. Actually, clear the entire workspace. I'm going to do this data set, and I'm just going to simply just go straight to the app. So this data set is linearly separable, but they will actually come very close to each other. Since it's a little bit more challenging. Oh, come on. So my column 1, column 2 are my feature space, column 3 is my response, my classification, and it looks like this. Last time we do in k nearest neighbor. One of the points, this particular point would not get trained, although I tried it on Tuesday, didn't work on Wednesday, it did work on Thursday, it's not working. Okay, so k nearest neighbor works only on Tuesdays and Thursdays, but any other day. It doesn't work on Tuesday, Thursdays. So the point is, for now at least, it doesn't work. Now let's see if this other version of it works. But one of the characteristics, one of the parameters, so in k nearest neighbor, there were two elements that you get to select. Number of neighbors that are going to be queried, and the distance that's going to be used in order to establish where are my 100 nearest neighbors in this particular case. Just quickly review. K nearest neighbor for any one given pattern that's unknown, it in this particular case establishes the 100 nearest neighbors in some of distance, and from those 100 nearest neighbors is established a consensus is on what is classification. If of the 100 near neighbors, 70 of them say you're class red and 30 of them say you're class blue, then it's going to go, consensus is that majority says that I'm class red, I'm going to go with it. 100 Euclidean. Now Euclidean to Mahalanobis, neighbors is always supervised. Actually, that's a good thing. Good thing to accidentally stalled on this because now I have to say about it. So until that point is becoming an issue. So in this particular case, it's not going to make a difference. I'm going to expand on it. I'm going to still stick to my claim that Mahalanobis distance is superior to Euclidean distance. I'm going to define and why and come back to this one and speculate why it's not working here. But moving forward, these classifications be focused on simplicity of implementation, be focused on how powerful they are, how well behaved they are. So we focus on one of those, all of those. And with k nearest neighbor, the comment was that, or one of the advantages is that there's no training to actually train a k nearest neighbor. It's just that during the testing phase, you have a mechanism that you can use the data that you have. But what I want to do, I want to ask you the question as far as the efficiency of the algorithm and more scalability to large data or big data. Comment on that. That how scalable is k nearest neighbor to large data sets? Is it as far as the k near, as far as when it applies to larger data sets? What are its weaknesses? outliers, but so when it comes to scalability, I'm not talking about the complexity. I'm talking about 2,000 becomes 4,000 becomes 4 million becomes 4 trillion. What computational complexity of this algorithm, how does it scale? Versus, for example, binary decision tree. Because why? You have to calculate the distance to every single element in your data set, and there select the top 100. Your data set, as the data set scales, every time you're testing, every time you have to go and check the entire, if you have 1 trillion data in your database, you have unknown, you have to take that one particular unknown, calculate its distance to all trillion data sets to see how close they are from length and select the top 100. And you can, this becomes extraordinarily expensive, and that's a single pattern you have to do that. In this pattern, you have to repeat all the distance calculations. It's extraordinarily time-consuming when it comes during actual utilization of it. Let's say, for example, by decision tree, that's not the case. You have a database of trillion points. It may take a long time to analyze it, come up with your decision mechanism, but once the decision mechanism is in place, when unknown comes in, you just subject it to that particular decision making and you're done. In this case, every single time you have to actually calculate your distances. You can now engage in potentially different derivations of k-nearest that may resolve that issue, but that's the problem with k-nearest neighbor. It has no training. It's very, very conceptually, and in fact, statistically may be very powerful, but computationally becomes very impossible when you deploy it to large data sets. So that's something not to forget. Now, what I do, I'm going to put this aside. I'm going to try with example 3, and from there, move forward. Then. So, are there any questions so far? So k-nearest neighbor scales very nicely to high near to dimensional to multi-dimensional space, because if your definition of distance should apply to all dimensions. This ends up a slightly different avenue that what is the distance, and believe it or not, there's an entire field dedicated to what is a proper distance. It's not just something you can fabricate distance in order for it to be a proper distance metric. It has to have certain properties. They have additive, for example. If I am away from the desk and the desk is 2 feet away from the other desk, that means it should be 4 feet away from the metal desk. So it should have triangulation, should work. So there are a variety of attributes that need to be qualified before a metric can become a legitimate distance metric. So I'm going to put this aside. If you don't care for it at this point, the question of dimensionality, in fact, is I'm going to address it when we get to the definition of Mahalanobis and Euclidean distance. What I'm going to do, I'm going to clear my workspace here. Here. Yes. I don't know if it is. Persists. In my example 3, I've tried to actually be more, come up with a more complicated version of things. New same structure of data. It's just more complex. So before we're clearly linearly separable. Now, this one, you can see that it is still separable, but it's going to be challenging because for example, from the binary trees perspective, if you try to draw a line vertically or horizontally, they're not just very easily separable. So what I want to do, I want to not worry about binary decision tree, but I want to focus on k-nearest neighbor. And nearest neighbor, it becomes a little bit more prominent as to those that are misclassified. And that a little bit later. But actually, it makes kind of sense for this point, for example, to be closer to the center of this cluster than to the center of this cluster in blue. For our general understanding of distances which is what I'm going to challenge. The point is a lot closer to a center of this guy than it is to the center of his own cluster. Therefore, k nearest neighbor, as we know, worked, and it worked okay. And just something else we have to do here. So what I'm going to do, I'm going to change the distance from Euclidean to Mahalanobis and run it again. Get 100% performance. And actually very substantial. And now I'm going to begin to ask the question of, well, how exactly is this Mahalanobis distance that it is making this assessment that this point is closer to that center, which is way up there, than is to this space that's here. So I want to put this on a pause, go back, and and at that point, I'm hoping it's going to make sense. So it's actually, I really like Mahalanobis distance. It connects to so many different elements in statistics and others. Slide. On the web, I was going to make it easy on myself, and I was going to just here go. Oh, okay, you're going to see Casey. Can you see the slide? My screen is saying what echoing is fine. I'm just curious to see. Okay, so is that yes to my question of screen, or is that yes to something from before? Okay. So solve by finding references on either Wikipedia or somewhere else. And oddly enough, they just overcomplicate this. I want to do I need a fresh screen. So next slide. Right here. So Euclidean distance if you have 2 points in space, point P and point Q, x2, x1, y1 as coordinates, and the coordinates of this guy x2, y2. Distance that you're generally calculating, which is this guy, it is simply square root of delta x squared squared. Right on. So Alex, can you hear me?
Yes.
Okay. Last time we couldn't hear anything. I wasn't sure whether. All right. Alex, I just turned off your microphone. There was a bit of an echo. So if you need to ask a question, participate, just remember to turn your microphone. This definition of Euclidean distance between 2 points P and Q, we calculated delta x, we calculated delta y, which is a change in x, is change in y. From there, we calculate a d. Or easier way, if I could use it as d squared to be equal to delta x squared delta y squared. Right, so I need more space than this. So deep. Okay, so if I have in a larger dimensional space, I can in fact the Euclidean distance in distance, so later. I can always write it as my d squared to be sum of xi squared, where x now is individual dimensions, so it could be x, it could be y, it could be z. If I have 5-dimensional space, I have in dimension 1 the delta x squared, and dimension 2 delta x squared, and so on and so forth. Now, a simple, so this is the Euclidean distance. Now, a simpler way that I can represent this is that every point in space can be represented by a vector with components x1, x2, all the way to xn. This is an dimensional space. Now, the Euclidean distance is nothing more than x multiplied by, or x transpose multiplied by, or multiplied however you want to look at it. This exact thing is going to provide everybody that I can say delta x is this, and magnitude of delta x, I mean Euclidean is just equal to that. So you can add them together, you can mix, multiply together by transposing and applying it. Do I need to demonstrate this, or if you want, I should move on? And use something. Damn, you said. Okay, so basically what I'm doing here, if you want to take the dot product version of it, so I can say delta x, the product vector is just nothing more than elemental multiplication of each other, which becomes xn squared plus x2 squared plus xx squared. It's just pretty much Euclidean distance that you take. The differences and multiply them, square them. Or so I can just put that. So at this point, whether you look at the square root of the magnitude, or you look at the magnitude or the square root of the magnitude, doesn't really make a difference. The point that Euclidean distance comes from that equation, you can either take it square root it or leave it as is. So I am going to is equal to my vector x. Utilize matrix multiplication, you will see y multiply x. And if I do it that way, this particular vector becomes x1 dot 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 xn by x1 dot 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 xn. Or if you know matrix multiplication, you multiply this out, you get exactly the same thing. All right? So I'm going to write my Euclidean distance. This generalizes very easily to the Mahalanobis distance. So delta is a vector. So a vector, when you're calculating its magnitude, the magnitude of the vector becomes this. When you apply that principle to what's the distance between 2 points, you establish the difference between the 2 points. That's called the delta x. It's the same thing, except one of them has a transpose. You don't nitpick, man. I mean, one got a looking x, the other one doesn't. Explanation there. Work with me. Okay. With this, you can, yeah. So. Those are the coordinates of a vector in an n-dimensional space. That. Okay. So a little bit more. So basically, what I'm trying to do, it doesn't really make a difference. And let me go into the base. I have a point here. I have a point here, right? Point here, I have x1, y And here I have x2, y2. Those are the Cartesian coordinates of those 2 points. Now, when you want to calculate the distance between the two, what you do, you create this inter vector. So this I am considering to be my delta x vector. And my delta x vector really is equal to x1 minus x2, y1 minus y2. There's differences. This is a vector. Now, the question is, what is the magnitude of delta x squared? That's going to be equal to delta x squared plus delta y squared. But just the case that I'm substituting. So if I was to write it this way, I'm kind of pushing this as it. So, but it represents the general idea that for any one given vector that has the coordinates x and y, I can ask the question of what is the magnitude of v squared, and that's going to be equal to x squared plus y squared. So this is the material. Now here, I'm going to claim that if we were to jump into an n-dimensional space, the seeming principles hold. Nothing, you don't have to change anything. Whereas delta x is going to be, so in this particular case, we are looking at 10-dimensional space. We have 10-dimensional vectors. So your x1, x3, on to x10 are going to be your coordinates, Cartesian coordinates in each individual dimensions. So you have 10-dimensional vectors. Now, 2 of them, to find the distance between you, you establish first a delta x vector, which is the pairwise coordinates of the 2 vectors subtracted from each other. And to establish the magnitude of that, you can either take them dot product them, transpose and multiply them. All of those are vectorial operations that give you the Euclidean distance between those point and n-dimensional space. So it's the exact principle. What you do, it even need to be, so the magnitude of a vector in a dimensional space is more than a dot product of the vector by itself or vector transpose multiplied by itself. And this is the main equation that I want to use in generalizing and move forward. That okay. I have to still kind of okay. So I am going to claim a little representation. If I was to take a point and ask myself, see all the points in space that are distance of d away from this point, what would be? Would be centered at point D. So this is right. For alternatively, roughly again, I am looking at x squared plus y squared equals e squared. I'm looking at all the points so that they adhere to this, except everything is shifted from the center, is moved to the center of the circle. That's Euclidean distance, the attributes that it has. So now, what is this disadvantageous? It assumes a change in delta x is the same degree of impact as a change in delta y. Both are equally as much penalty, as much advantage. They are equally weighed. Now, I submit to you that if your is it this way, data is that way. So, the center of your ellipse. Now I asked you the question of how likely is it in this distribution with this center, I observe a point here. First, how is it whether the one that this one would be an outlier, more of an outlier. To be an outlier. Give me an ellipse in the center of the ellipse. With the 2 points, mark them in X to be more likely to be an outlier. The one on the right. Because of all of those reasons, the idea here is that the distribution of data, if I was to quantify how much is the variation of my data in one dimension, whereas this much. And if I was to proportionately report the distance from the center of the ellipse, properly scaled based on the units of variation, that is above is about a 1 whole unit of variation is away, where one that's to the right is a fraction of the variation away. So if I was to scale the variation of my data, this distance measurement, then it is clear that it is far away from the center than the other one. Euclidean distance would give you exactly the opposite, exactly the point. So if you based on Euclidean, the above is far closer to the center than the other one. Whereas you put it in the context of the variation of your data, then it flips. So the Mahalanobis distance then becomes appropriate because you are taking things in context of what your data is doing. And if you wanted to think of it different, it's just a stretching of the space. If it is the case that you have a circle, and you can imagine you have drawn your data on a piece of plastic, and you take that piece of plastic and stretch it, it would be this kind of a phenomenon. So you kind of need to know the stretching and perturbation of your additions in your data. So the mission is, how would you calculate this? How do you come up with a unified way of representing this? That becomes Mahalanobis distance. So to just speak to that, get to the point. I have to change it again. So Mahalanobis, general representation of Mahalanobis distance becomes following. Given 2 points and a magnitude of a vector, given that belongs to an n-dimensional space, Mahalanobis distance is calculated by x times, and this is matrix operation, the scaling factor inverse times x. And I'm pulling sigma because really represents, generally in statistics, represents variance matrix as related to the variance matrix. It exactly kind of represents that. In the special case that if your sigma is identity of 2 dimensions when n is equal to 2, it becomes sigma becomes the matrix that's 1, 0, 0, 1. If you multiply this out, this is an identity. This converges to transpose times x becomes Euclidean distance. In the case where sigma is, for example, let's say it is 2, 0, 0, 1, you can see that the proportional spacing and weighing of the dimensions of the first one is represented. The first one is scattered twice as much as the first one, and during your calculation of the final notation of your distance, the proportional difference is going to come into that calculation. So what this does now, so given your data, you can always calculate sigma, which gives you the relationship of variation in different dimensions. So it's not just a variation in each dimension by itself. It's not. And in fact, where I am going to take it connects to that. If you were to take this, and this becomes a bit too mathematical. I didn't mean to take it this far mathematics, but from here, they'll come here on your chest. So in this case, in the case of identity, basically what you have, if I was to represent the sigma to be equal to A00B, this, if you use it, will get the equation of x squared over A squared plus y squared over B squared equals B squared. If A is equal to B, you arrive at the circle. If A and B are different, you arrive at an ellipse that it is distorted by proportionally based on A and B. But so Mahalanobis distance has yet another advantage, which is what I want to kind of discuss. In fact, this is my opportunity to switch these guys around. Yeah, these two around. Okay. Now, the slide, and from here I'm going to start current. Now, when I have, for example, sigma, go back. The case of sigma is equal to A00B, this is convert my distribution, my measurement of that distance into ellipse. Actually, this is kind of like A, this is B. Now, what I can say sigma is equal to A, B, C, D. So the diagonal elements are no longer 0. What this is going to do is going to convert things into a fit ellipse. How you get your sigma is directly related to actually a variation, covariance, variance of your data. But to actually properly distribution of your data, variance in your data, what you should go to a full calculation of variance matrix. And I'll say this and I'll stop with the just one minute. So to calculate the variance properly from your data, from that then calc and perform Mahalanobis distance based on dimensionality distortion that is presented by your data. For each one of your classes, you calculate its sigma, use that sigma to measure the distance between a point and that particular cluster. You can always see, like, this may be one cluster, be my second cluster. Now the question is, this point is how far away from individual clusters. It's not really that easy to answer. This is the center. This is the question is that point X is closer to the center of each one of the dimensions. If you were to implement Mahalanobis distance properly, you could calculate the distance between X and ellipsoid center on the variation. Same thing between X and the center of the. That's going back exactly the reason. questions. Alex, I'm sorry, I'm kind of this thing a little bit more than I needed to, but are you okay? Well, I didn't hear anything, so if you can send a chat, let me know you're okay. If this is not, I didn't mean to get this much into detail in mathematics. I'm going to come back a little bit. Okay, all right. I'm just going to come back more to functional machine learning. But what about people here? You guys all right? So tie, you have to come up with something heuristic. What you can do then, you can say if there's a tie, it makes sense to break it off. I would say go based on the probability or the population of the data. If there's got more points than the other one, then go. That then, if I was to now put this aside, I mean, this is a distance measure of distance, whether the difference between Euclidean and Mahalanobis distance. But any that you see that there's a measure of distance, you should be able to, there should be some option of selecting the Euclidean distance or Mahalanobis distance. Or as far as I'm concerned, universally, there is no reason why not to take Mahalanobis over Euclidean. Mahalanobis is a more general case of Euclidean. So, but, so, okay, I think I know what you're asking, so let me go back here. The measure of distance, okay. Okay, so first let me just do this. So in this particular case, you see that the distance is, so this is k nearest neighbor. If you go to distance to the advanced options, Mahalanobis is a distance. There is Euclidean is a distance. There's also city block that's commonly used. From then on, everything is kind of esoteric. There's Chebyshev, there's Hamming distance. These are a little more esoteric, but their own place. I will mention as we go along if opportunity arises. But let me see if I can get at the core of what Jared is asking. You're expecting that somewhere behind the scenes, there's a ellipse put on top of data that embodies class 1 and another, some sort of ellipsoid put on class 2 that it is, that embodies, that encapsulates the class 2. And by the way, all of these principles extend into n-dimensional space. We put it in a 3-dimensional space, whether you put a sphere or football-looking thing around your data. In 4-dimensional space, the same thing extends. You can't visualize it, but dimensional is very extendable. Hyperdimensional sphere or hyperdimensional ellipsoid can be put in any data set. Am I correct, Jared? Your question is related somewhere behind the scenes. There's a ellipsoid that's fit to. So the measure of distance is ellipsoid, if you use Mahalanobis. Interesting exercise will be this. I will try to actually perform this exercise today and come back. So you have trained your entire network. The Mahalanobis distance that is presented here, right? Now the question becomes, how does the rest of the space, what is the delineation that the algorithm is putting together, where it separates the blue and red? And our brains, we are thinking, it's got to look ellipsoidal. But not, in fact. There is some sort of ellipsoidal thing in place, but it is not. So, for example, the question, I tell you the exercise, and if you want to go perform it, then I'll do it later on, I may present it tomorrow. So the entire space that you see, a grid space that goes from 3.5 to 7, and from, I don't know, 10 to 17, it creates every point in this grid, just artificially generated points, right? And then pass it through this particular classifier that you're trying to ask it. Am I class blue or red? And that will now give you the boundaries that it has internally placed in order to decide whether something is class blue or class red. And the point becomes clear if you start thinking of a point out here. Where out here belong to blue or red? Blue. So at that point, then it becomes maybe, so what about the point way off the screen? So then, what about the point here? See that now it becomes not so easy to see, but perform the exercise and see what comes out. In fact, you may find it to be surprising. Next time. I consider this the end of k-nearest neighbor, k-means string. K-means clustering issues, right? So k-means clustering, you have to calculate a distance, which the distance can be Mahalanobis or distance. So any questions related to any of this stuff? Okay. No. So K means clustering versus k-nearest neighbor. In k-nearest neighbor, there was no training. You say, who's my 10 nearest neighbors? What do you think? But k-means clustering is different. You take your data and condense it to knowledge, where the knowledge is represented by the centers that you have. So new data point comes in. You don't compare it to the trillion of data that you had to create the clusters. Measure the distance to the center one, to the center two, whichever one it is closest to, that's to what we belong. It's computationally far more plausible. It's a deployment to large scale than k-nearest neighbor. K-nearest neighbor can be very potentially powerful, but it is very limited in deployment data. Prediction. Yeah, so I'll repeat what I had yesterday, but I had it this morning. So k-nearest neighbors, whether you're doing prediction or classification, it starts by saying, who are my k-nearest neighbors? So now you identify the k-nearest neighbors. Now you can the point is not predictive. So for example, in this particular thing, in the example that I gave yesterday was I'm going to try to predict based on shoe size and I asked two questions. One of them is that am I a guy or a girl? That's classification. So so who are my nearest neighbors? So I find the two nearest examples in my data set. The nearest to me based on their shoe size and weight. Now ask the question of, are you girls or are you boys? On that basis, decide I'm a girl or a boy. Or I can decide what height from all the 10. I'm there, collect all that information, from there take an average and say, oh, it seems like I should be about 5'7". No. Shoe size weight was. Each one of my knowledge sets, they have also their output data that's actually associated with them that may be the classification, categorization, or their output value. I ask the question of how high am I? So it does have it, but depending on how you're forming your question, you can use both. But classification, for example, you can. The questions with k-means clustering can do the same thing. They are very similar to each other, right? Even names are kind of like overlap quite a bit. The question is, I'm asking you guys, can you use k-means clustering to predict prediction? How you would do it. Classification is easier, right? Like go back again to boy, girl. You separate them, put a cluster, you can put a mean on which one is a female clusters, put centers, and now I can see what I'm closer to on the side whether I'm girls. That's easy. What about so what would you need to do if you were to reformulate the problem such that you want to deploy some sort of a classification or prediction using k-means in new-style clustering? What you would have to do, you have to create individual clusters. So you may have to say, I'm not going to be able to get exact number of how tall I'm, but I'm going to create a cluster of people that are 4 foot, cluster of people that are 5 foot, cluster of people that are 6 foot. And you can ask the question of, am I 4, 5, or 6? So you can see how you can now say, okay, it's 4, 4.5, 5, 5.5, 6.5. You can kind of define clusters and then redeploy k-means clustering to sort of do prediction, but really what you're doing, you're not doing prediction, you're kind of using, models in order to fill in the gap and do some classification. That's figures.
Two different classes would have different sigma.
They may, but in this particular case, the way I generated them, they do not. They have sigma values, they're just twisted. But this becomes a cool thing. You can actually look at it if you want. You can generate your data as you want. I generated X and Y in random distribution. So you generate X and Y from a random number, no random distribution. Took Y and squished it by a factor of 0.3. Okay, now my distribution is not circular, squished, 0.3. And that will generate this. But to put the twist in what I did, I generated an X and Y distribution, and I multiplied it by a matrix of, I don't remember what it was. It was something like maybe 1, 0.5, 0.5, 0.3. The fact that the two off-diagonal numbers are the same thing would basically put it at the 45-degree line. The fact that the off-diagonal numbers are 1 to 0.3 kind of approximately proportions it that way, but it's not that simple. Formally, methodically, it's a different thing, and we can talk about that at some point later.
So, like that blue dot way out there, you're trying to get more classes, put it into the equation for the blue dot and provide see which one is the best.
You would put the data point. You would look at so you would measure this distance to the center of the cluster, given cluster property center and its distribution, its variance, and then you would calculate the distance of a known point to the red, using the properties of red, the center of the red, and the variance of the red. You would get two numbers, and with those two numbers, you would make a decision on the basis of which one is bigger. So if you were to do it in MATLAB has a very easy way that once this is actually trained and it's an object, you pass it to the object and it gives you all of those things behind the scene. But if you were to write your own program, that's what you would do. Let me just start the neural network portion very quickly, and I'm going to use 5 minutes for that one, and then from there I'm going to move on. I'm going to do a demonstration of the network. I'll do the demonstration of neural network tomorrow, the big neural network, and what is left over, I'm going to record from recording session independently and upload it to YouTube. Not been translated yet, so I am done with the R workshop. Everything is uploaded. So I'm going to start converting these to YouTube and putting them up. Hope it'll be up there. The neural network, I just want to put the network, what I want to do, artificial neural networks are inspired by the biological neural network. There are many advantages of why to do that. So, but just quickly to you, a neuron be represented by all the inputs to the neurons or biologically the dendrites will be presented by inputs x1, x2, ... xn. These take n inputs. we just mark it as output, or VY, output. Every one of the connections, so it's the axon output of the neuron, body of the neuron. Every one of these weights has activity, so W1, W2. The attributes of W are that they are continuous numbers between negative infinity and infinity. They can be any number. The larger the number, that means more, that particular input has more impact on the output of the neuron. The weights can be positive or negative. If it is positive, it's said that that particular input is excitatory. If it is negative, it's called to be inhibitory. So what this network does, neuron also has a firing threshold. So what neuron does, it applies every of the inputs corresponding weight. Therefore, if the weight is larger, it's more important, it's more contributing. If it is smaller, it's less. All the inputs are more multiplied by their corresponding weights of all I, are summed together. And the neuron fires, produces an output of 1. The entire sum is greater than or equal to the value of the threshold. Otherwise, it remains dormant if it is at value of theta. If W is positive, contribute to stimulation of the neuron and get you closer to the theta, when the neuron will fire. If the weight is negative, it's going to subtract values and it's going to prevent from neuron arriving at its firing threshold of theta. Of you that may know, this is an equation of a plane. In a two-dimensional space becomes line, in a hyperspace, in an n-dimensional space becomes a plane. Everything we have said applies here to neural networks, except we have a very specific advantage over all the ones that we actually looked at this time. What I'd like to do is I will demonstrate this quickly this time. There, I will defend what exactly neural networks can do. I may just try to be brief about it. So if you guys don't have a question, I'm going to stop at this point. I will see you guys tomorrow. Questions? Alex, are you still there? Or Alex? Right, well, stop sharing. Leave the meeting.